talking about the collision model based on chemical kinetics. So this model is built around the idea that molecules have to collide in order to react. So this explains the dependence of concentration and temperature for reaction rates. Concentration, because the more concentrated it is, the more molecules are in there, so the more higher probability of hitting each other. And same with temperature. When temperature is higher, they're moving faster because they have more kinetic energy, so that makes it more likely that they will get in contact with one another. So if molecules are constantly colliding, why do only a small fraction actually produce a reaction? Spontaneous proposed the existence of what's called a threshold energy or activation energy, labeled as EA, that needs to be overcome in order to produce the chemical reaction. So this is a graph that shows how much energy is needed to actually disrupt the reactants and make them into the products. So the change in the energy represents the net change in energy in going from a reactant to a product. And the second side, the right side, the B side, is just talking about a molecular representation of what the reaction is happening. So at the top of the peak or hill was what we call the transition state. And this is found when the reactants have moved around, but they're not quite where they're supposed to be for the products yet. Exothermic is indicated on this graph when the products have a lower potential energy than the reactant. And then endothermic happens when the products have a higher potential energy. And this makes sense because we know that exothermic means release heat and endothermic means gains heat, so it would make sense to follow this trend. The main point here is that a certain minimum energy is required to get over the hill so that the products can form. So the rate of reaction depends on the size of the activation energy, labeled EA. So some requirements for them to collide successfully and to rearrange. The collision must involve enough energy to produce the reaction. So the energy from the collision must equal or exceed the activation energy. Otherwise, they're just going to hit each other and bounce away. And the relative orientation of the reactants must allow the formation of new products necessary to produce the products. So any new bonds that need to be formed. So we have the Arrhenius equation, which we don't always use it in that form, but if you take the inverse of the E, where A stands for the frequency factor, EA is activation energy, temperature is in Kelvin, and R is our value of 8.3145, and that's because that's joules per Kelvin mole. So temperature has to be in Kelvin when you use this. If we take the natural logs of both sides, then we can get rid of that e to the x function, and it actually sets up really nicely into a linear equation where the slope is equal to the negative activation energy divided by r. And so that's nice for when we have to graph things. We can get a linear equation, and then we can find slope or find the activation energy. This equation is not in your notes, but you need to write it down because we need it for example 8. This is the comparison of two different temperatures and two different rate constants. Notice the differences there. So in example 7, we have this information. We have the values of K, and we have the temperatures that they were found. So we need to calculate the value of the activation energy for this reaction. So we need to graph it to be linear, and then when we have a linear equation, then we can solve for the activation energy when we know the slope. So going into Google Docs or your graphing calculator, if you would rather, we need to first get the temperature into Kelvin. So I'm just going to do it on here. If you want to do it manually, that's fine. But I'm going to take 273.15 plus my original temperature. And then the nice thing about that is you can just drag it on down. And this is showing everything in scientific notation, but that's okay. And then we also need to take the inverse of the temperature. So we're going to take the inverse of the Kelvin temperature. And the reason why we had to change it to Kelvin, honestly, is because you can't divide by 0, and we might have had a temperature of 0. So taking the inverse of each of those Kelvin temperatures, I now have data points for the inverse of temperature. That is going to be our y, or excuse me, our x for the graph. And then for the y, we need to take the natural logs of the k's. So type in ln, and then highlight that, and go ahead and drag that down. So now that we have those two bits of information, we first need to highlight the inverse of T column and then control inverse of, or the ln of K, making sure not to highlight those two top points, otherwise it will not want to make your graph nice and neat. So to zoom out a little bit so you can see the graph better, go to Insert, Chart. We're still going to do a linear chart graph like we've done before, and then we want to use column C as headers, and that will make us our nice pretty straight line. So just to give myself some information, we took the inverse of temperature versus the natural log of K for here, and the horizontal axis is our inverse of temperature, and the vertical axis is the natural log of the K, just so it looks nice and pretty when we insert that graph. So since we have our straight vertical, or excuse me, linear function now, let's go ahead and solve for slope. So slope is the change of y over change of x, correct? So I'm just going to take two data points, and I'm just going to do it all in here instead of writing everything down. So I'm going to do the first and the last. Why not? So the last ln K minus the first ln K divided by the last temperature inverse minus the first temperature inverse. So we get that to be a slope of negative 1.22 times 10 to the positive fourth. Okay? Well, that is not our end result. That is our slope, which, remember, from our linear function that we said the slope is equal to the negative activation energy over R. Okay? Well, now we're going to plug in and solve for the EA. So I have my negative 1.22 times 10 to the fourth is equal to negative EA over R, which is the 8.3145. The negatives can just go away, and then I'm going to have to multiply over the 8.3145, and when we do that, the activation energy is equal to about 1.0 times 10 to the fifth. And the activation energy is going to be in joules per mole, because our value has joules per mole Kelvin. And that's it. That's our answer for example 7. Now for example 8, we are going to do something a little different. So for this reaction, at 550 degrees Celsius, the rate constant for this reaction is 1.1 liters per mole second. And at 625 degrees Celsius, the rate constant is 6.4 liters per mole second. Using these values, we're going to calculate the activation energy for the reaction above. This is a case where we're given two temperatures and we're given two Ks. We don't have to solve for K. It's already given to us. And so this is where we're going to use that other equation, okay? Where I'm going to go ahead and just label the first as my 1, the T1, and the second temperature as my T2. Okay? But we need to change those into Kelvin. So T1 changed into Kelvin, yes, I know we still have to change into Kelvin, is 823.15 K. And the second temperature changed to Kelvin is 898.15. Okay? So plugging into that other equation, which remember, it's the natural log of K2 over K1. So the K2 will be the second, 6.4, over the first, which is 1.1, is equal to the positive activation energy over R, which is 8.3145, times the inverse of T1 in Kelvin, 823.15, minus the inverse of T2, which is 898.15. So now we just have to do a lot of solving to get our EA, and I'm going to let you do that, but when you do that, the EA is equal to, the activation energy is equal to 1.44 times 10 to the fifth joules per mole. If you need help with your algebra, let me know. Alright? But just to save time, I'm not going to go through that. So, two different ways to use the two different equations. It's really just plugging and chugging as long as you can read where everything is supposed to go. So now, with our collision model, we have to talk about catalysts. So we've seen that raising the temperature can increase the rate, but sometimes that's not feasible. For example, maybe you don't want the temperature to raise, otherwise something bad might happen. In our bodies, we have enzymes, which increase the rates of reactions with our biochemical processes in our bodies. So a catalyst is a substance that speeds up the reaction without being consumed itself. So in the graph pictured, you can see how the uncatalyzed pathway for the reactants and products has a much larger peak or hill versus when the catalyst is added in. And that's great because with that catalyst, you don't need to have as much energy. It lowers the activation energy for the reaction. So reactions tend to happen a lot faster and a lot more often. Catalysts can be classified as homogeneous or heterogeneous, where homogeneous is one that's present in the same phase as the reacting molecule, and heterogeneous is when it's in a different phase, usually in a solid. So like sometimes you'll have like a platinum surface that it reacts on or something like that. The heterogeneous catalyst most of it often involves gases reacting or being absorbed on a surface of a solid catalyst. So adsorption refers to the collection of one substance on the surface of another substance. So absorption, because there is a difference there, refers to the penetration of one substance into another. For example, water is absorbed into a sponge or by a sponge. Adsorption with the D refers to the collection on the surface, not being penetrated within. So some steps of heterogeneous catalysts, you have the adsorption and activation of the reactants, the migration of the absorbed reactants moving on the surface, the reaction of the adsorbed substances, and then the escape or the desorption of the products. Homogeneous catalysts are in the same phase, and so these happen both in gas and liquid. And like here in this picture, I have a picture of ozone on their Earth's surface. So there are catalysts in the atmosphere that are making the gases in the atmosphere react and make ozone, O3, or other potentially harmful gases. And so those catalysts are actually in gas form as well. So that would be a real world example of a homogeneous catalyst. This is the end of our Chapter 12 notes. Please refer to your checklist to know what problems to do for your assignment.